the common interior of r equals 4 sine 2 theta and r equals 2. All right, so again, there's a lot of ways that this could be easier than what I'm about to do. If I allowed you a calculator, you could just graph both of those in your calculator, assuming your calculator's in radian mode and assuming you know how to change it to polar mode. If you have a calculator. I'm going to assume that I don't have a calculator here, although I'll probably use one at the end of the question anyway. So r equals 2 is probably the easiest of the polar graphs to do. It's the circle where the radius is always 2. So no matter what theta is, r is 2. And then the other one that is much tougher is 4 times the sine of 2 theta. Now there is a hint here. The fact that this is a 2 there and that's an even number tells me that there's 4 petals. So if you know that, you really have to do a lot less graphing before you can figure out what it looks like. But you probably also need to plug in some points. You plug in 0, you get 0. Sometimes I think of it like this. What's the biggest that sine can ever be? Right, so if I can make this to be as big as possible times 4, the biggest r in this question is going to be 4. So what can I take the sine of? Don't worry about the 2. But what angle can I take the sine of that would give me 1, the biggest sine value? Okay, so if I want to take the sine of pi over 2, what angle can I double to get pi over 2? Right, so pi over 4, I don't know that I guess you don't have to test that point, but that's a pretty useful one. So in the middle of this quadrant, it's going 1, 2, 3, 4. And because I know that this has 4 petals, again, I can not really cheat, but I know it's going to be symmetrical. It just allows me to do less points. So there's nothing wrong with doing more points other than it's tedious and time consuming. But more points is always going to make you feel more confident about your graph. Okay, so we are got to read the question again. Find the total area in quadrant 1 that shares this common area here. So here's the area that they share. And we are trying to find that common area. So I'm certainly going to need these intersection points. And this is probably hard to see, but I'm thinking this probably needs to be split into 3 parts. There's this part where the area is bounded by a petal. There's this part that's bounded by the circle. And then there's this part that's bounded by the petal again. So I see 3 sections. So if I'm trying to find that area, I would personally just make 3 of these. Of course, you better make sure you know the formula. And I don't have today's daily meme up there, but the daily meme is making fun of that it's easy to forget the 1/2 out front. Okay, so again, it looks like the first area is trapped by the petal, and the petal is 4 sine 2 theta, so that's the first r I want to use. This last little bit of area is bounded by a petal, so the last r is going to be 4 sine of 2 theta. But in the middle, it's trapped by the circle, and that radius is just 2. Okay, still okay? Okay, so then I need to figure out some angles. So this one here, I don't have my table over here, it's off the screen here, but I did start that at 0 and it gave me 0. So 0, and then I want the angle to get a little bit bigger, but not for very long, because as soon as it gets to this intersection, the area stops being bounded by the pedal curve and starts being trapped by the circle. So I need to figure out where that is. So we could set the two equations equal to each other. Think about where sine is a half, which is like pi over 6, but I'm going to double that, so I actually need pi over 12. Pi over 12 times 2 is pi over 6, and the sine of pi over 6 is a half. Now, the nice thing is that this is where this area stops and this area starts, so I get to double dip at least. And then it keeps being trapped by this area until I get to this intersection, which is the next time where those are equal. So the next time where sine is a half, which is 5 pi over 6, but I'm going to multiply it by 2, so it's actually going to be 5 pi over 12. So if I plug in a 2 in there, 2 times 5 pi over 12 is pi over 6. The sine of pi over 6 is a half. So that was the next time that sine was a half. So it stops being this one and starts being this one at 5 pi over 12. And then finally, it goes back to being the red function, red polar curve, and the angles keep getting bigger and bigger and bigger, and it looks like they're trying to go until they're pointing straight up. So I think this is probably 0 in the pi over 2 direction, but I would actually plug that in and see. So if I plug in pi over 2 into that R equation, I get 2 times pi over 2, which would be pi. The sine of pi is 0, times 4 is 0. So pi over 2 is what I suspected, and it matches up. And please make sure you guys are also practicing typing the integration in the calculator. So I don't expect you to do this level of integration by hand, but if you're not practicing putting it in the calculator, you're probably going to miss or you're likely to miss like not typing it in correctly. So you need to make sure that there's not some kind of mistake that you're making. And while I say all that, I am typing it in also. Squared. Calculator needs to be in radian mode. And my calculator tells me this is about 2.457, which matches up with what they got. Okay with that? And again, this is why I said the 9.8 is even easier, because if you can split this into 3 parts, find the angles to each part 3 times, use the formula for area 3 times, then surely you can do the questions in 9.8 where you just have to do it on one and there's no intersections and not multiple parts and stuff. So that should make those significantly easier. Okay, I'm assuming he is not the only one that was going to ask about question 3. So do you guys have another or something more specific about 3 while it's still up? I guess let me ask real quick, is the hardest part of these for you still the graphing? Like figuring out what the graph looks like, or what part do you struggle with the most? Just for my own. These? Yeah. On questions like these though, when you need an intersection, at least you can get an equation out of it, which is nice.